Yeah, so this talk is going to be about reductions in network information theory. And I think it was kind of challenging to prepare the talk in the sense that, first of all, it's a little bit an outsider in the sense of area from this workshop, but I hope there'll be things that will relate to the audience. Secondly, the audience is sort of mixed, and so some things are going to be trivial for one audience and non-trivial for the other, and vice versa. And thirdly, so this is on now for sure, but that's too strong, isn't it? Okay, good. And the hour. So this talk is going to be very high level. I don't want you to fall asleep too much during the talk. So I'm going to talk about network information theory or network communication, and this is a very sort of rich and intriguing field of study that has seen a lot of progress over the last decades. But I think it's fair to say that there are a bunch of very central problems that are completely open. And just some examples. So understanding the communication rate or the capacity of a network in which all its links are noiseless, so just communicating over bit pipes with no noise at all, this is called network coding, and this is not well understood at all. It's very, very open. Communicating over a network in which maybe links are noisy, or maybe there are components, local components that are noisy. So you can think of a multiple access channel as being something inside the network, or a small broadcast channel with noise. So networks with these components that are noisy is completely almost out of reach. So no one is sort of addressing this seriously because it's completely open. And the reason is that even these very local components inside a network, for some local components, the rate of communication or the capacity of these small objects is not understood at all, or not well understood. So there are many problems, and they're all and many of them are open. That's sort of the idea. And what happens is that many times, if you look at these individual problems, then of course they're all in communication, so they have similar proof techniques. But to some extent, each problem is sort of on its own. It's individual, and you have to sort of address its problem with its own theory. So the theme of this talk is to sort of try to find some kind of unifying theory that'll look at the network communication problems as a whole and try to identify similarities and differences in their solution. So that's sort of the goal of this line of study. So towards a unifying theory. So again, these individual studies are very successful, or have been successful, but sometimes they haven't solved the problem yet. And what I'm going to address here is something that, for one community, it's actually the bread and butter of that community in a theory of computer science. But for the other community, for the information theory community, this is not well studied. So I'm going to talk about not individual studies, not direct studies, but conditional studies. So instead of focusing on a problem and trying to solve it, what I'm trying to do is relate between different problems, understand the implications of solving each and every problem, and I'm doing this through the very simple idea of reductions, right? So if I have a network communication problem N1 and I want to solve it, then the way to solve it sometimes is to reduce it to another problem. This problem is now N2, in such a way that if I solve N2, then I solve N1. This means that I'm taking problem N1 and reducing it to problem N2. Again, a very simple idea. In the theory of computer science, this is really used a lot. In crypto, it's used a lot. And in information theory, it's not used that much. And the strength in this idea is that to connect between two problems, I don't actually have to know how to solve either one of them, but I can still connect them and understand the implications of the connections. So again, this slide is highly trivial to some audiences. In general, what do these reductions give us? If I can take a problem and reduce it to an easy problem, then this problem becomes easy, of course. If I take a hard problem and reduce it to some problem N2, in the sense that solving N2 is going to solve the hard problem, then this means that problem N2 is a hard problem. These reductions allow the propagation of proof techniques, of course. And just studying reductions as a goal gives us new, I think, intriguing and interesting problems or questions that are not have not necessarily been addressed in these individual or in the mainstream of information theory.
Do you hope to find central problems, like a problem to which many other problems are reduced to?
That's done. I'll do it already here. Good. So, these reductions give a structure to the field, and you can think of all the communication problems as sort of these dots, and these abstract dots, and you get clusters of problems that are related, and you can identify maybe these central problems, just like NP-complete problems, and so on, that will, solving them will solve others. So that's the general idea. The general idea is to take this well-studied theme of structural studies of a family of problems and to apply it to network information problems. And there have been a bunch of connections that have sort of arisen recently in the last 2 or 3 years. Connections between index coding, which is a form of network communication, which I'll talk about a little bit, and network coding, which is communicating over networks with no noise. Connections between index coding and interference alignment, which is some kind of wireless communication. Connections between, again, index coding and distributed storage. Connecting, I'll say these and I'll elaborate a little bit more, between communicating in a multiple multicast setting in which sources may be source information may be wanted at several terminals, to communicating in a setting in which each source is sending its information to one terminal, that's multiple unicast. Even taking that to a setting of 2 unicast, communicating securely and communicating non-securely, these have also been connected, communicating with errors and with no errors. Again, so many connections have been sort of come up in the last few years, so I'm going to discuss some of them. And I'm going to focus on the task of network coding throughout this talk. And I'm going to focus on a certain problem, which I think is very appealing to introduce, which is very simple to state, which is called the edge removal problem. So that's sort of the plan. And of course, feel free to ask in the middle. So I'm going to talk about network coding. So I'm going to give like a 3-slide preliminary to what I mean by network coding, and then I'll go on from there. So an instance of this network coding problem is a directed network with links between nodes. These links don't contain any noise at all. There's a bunch of source nodes that generate information, a bunch of terminal nodes that want to receive information. And you can think of a matrix of requirements, which terminal J wants information from source I. So the requirements can be completely general. And the objective is to design some kind of flow of information over this network in such a way that at the end the terminals can decode. So that's the generic network coding problem. And some kind of simplifying assumptions I'm going to make in the talk. So I'm going to think of a cyclic network. So there's going to be some kind of direction from the sources to the terminals. So there's no cycles in the networks that I'm going to discuss. And some results generalize, some don't. The edges are going to be capacitated, so each edge has a certain capacity, a certain amount of bits that you can communicate over it. So we're going to denote these by C of E. Through most of the talk, this is going to change here and there, I'm going to consider sources which are completely independent. So each source has you can think of it as being a random variable that's uniformly distributed over some space. Each source has an independent random variable, and now you're sort of communicating through the network, and you want the terminals to decode. And also, in most of the talk, this will change a little bit here and there. I'm going to think of the multiple unicast communication requirement, in which we have k sources, k terminals, and source I wants to communicate with terminal I. So that's the idea. OK, so what does it mean to communicate? What does it mean to communicate at a certain rate, R1 to Rk, Ri for source I, over a network, which is this instance n, and these sources Si and Ti. And I'm going to communicate with block length n, so we're doing things over time. So they have a block length n, and I'm going to communicate allow an error epsilon. So this rate vector R1 to Rk is achievable with these parameters n and epsilon if the following holds. If there are these random variables for the sources, and random variables xe for each and every edge, such that the following things happen. So first of all, you want each source to have a high rate random variable. So it's going to be a random variable which is uniform, independent of the others, and its entropy is Ri times n. So again, I'm going to revisit this independence later, but having entropy Ri times n just means that I'm uniform over this 2 to the power of Ri times n messages. That's each and every source. And each and every edge is going to have a random variable. This is this xe, and xe is thought of as the value that I'm communicating over the edge. And again, its support is going to be a support that I can communicate over this edge in n time steps, so it's going to be of support 2 to the power of c times n. And I want this to be a flow of information over the network. So what's happening is this information is sort of propagating throughout the network, and at each intermediate node, the outgoing random variable xe is a function of the incoming random variables. It can be any function, but it's some predefined function which defines sort of how the flow of information works. So I have rate, I have edge capacity, I have functionality, and at the end the terminal gets a bunch of incoming information. It wants to decode. It's going to decode to some SI bar, and we want SI bar to be equal to SI with high probability. So we're going to say the communication in this n block length sense is successful if the probability that all terminals decode correctly is at least 1 minus epsilon. And the only source of randomness here are the random messages, because the functions are, just a second, the functions are defined as part of the communication protocol, and they'll be deterministic. So we want, with high probability over the messages sent, we want communication to succeed. Yeah?
Does it matter if you could think of it as a bit-by-bit transmission, or as sending a whole string and then encoding it? Does it matter which way you do it?
Yeah, so you can think of this as sort of a one-shot kind of problem, which you're sending just bits, and you're doing all the encoding, and at the end you want to decode the ith bit at time I, or even based only on the information you get at time I. And you can think of this as a block length manner in which you're communicating, and you want to decode only after the entire communication, and you can have things in between, and they're different. These will make a difference.
How is error introduced in these epsilon?
So I'm just saying that you can communicate with error epsilon if I give you a communication scheme which is just these functions at the internal node that take incoming information and give me outgoing information, such that with high probability over the source information, at the end each terminal will decode correctly.
But an individual, all of the messages are decoded correctly?
So the way I define it here doesn't really matter, because n, which is the parameter that's asymptotic, is actually the block length, and the size of the graph is thought of as something constant. So you can have individual terminals decoding correctly and union bound over them, or you can have all the terminals decoding. I'm just doing all the terminals decoding correctly.
So it's similar to multi-commodity flows? Yeah?
Very similar, yes. So multi-commodity flow would be one kind of communication scheme in which you're sort of assigning a flow to each and every source of information, which means that you're not encoding any information in the middle. You can, in this scheme, you can take information. You can think of one flow entering here, one flow entering here, and then this is sort of a combination of these two flows. They're not preserving the flow.
There are some examples when this is not optimal.
So there are examples where multi-commodity flow is not optimal, yes, and that you need encoding.
Does it matter if the function is random?
Say it again?
Does it matter if the function is random?
So there are communication schemes in which one would consider random functions, and this sometimes gives good results, sometimes it doesn't give good results, depending on the communication setting. In this setting, which is multiple unicast, it's actually not that good of an idea. Yeah?
Does it capture things like broadcasting, where you, like in the traditional network communications, when you have multiple same sending but different noisy versions of the same thing?
So here I'm assuming that all the links are without noise. So was that the question? If I
No, but like this model where it captures things like I'm speaking and different people hear different noisy versions, so I really cannot control independently a message message you across different edges.
Okay, so you're asking if a node always sort of broadcasts the same information to all the outgoing links, or they can do different information to different outgoing links. That's the sort of question.
For the wireless setting, you just speak and then you would hear
Yeah.
different. And
This is strong enough to model the wireless setting because you can think of an internal node having only one outgoing edge, which then branches out to all its neighbors, and then
neighbors might hear different things, right?
But if this, if they're all of the same capacity, the outgoing edges, then you can sort of predefine what's going on to all the different edges. So this would capture wireless.
So this would capture the classical broadcast channel from this.
No, but there's no noise. There's no noise here.
Because you know, the receiver knows exactly, for example, the receiver at FE knows exactly that X1 will flow from here, that another flow comes from X2, and then whereas wireless you don't know.
There's no mixing. So again, the information is sort of coming in, but if information comes in simultaneously, it's not mixed in the air or something like that. It's not. There's no mixing going on.
Yeah, it's Mac, but forget even the Mac. I'm just looking at the broadcast. So there's no, it's just a three-terminal network, and there's one sender, and there are two receivers.
Mm-hmm.
And the sender is just shouting out, and the receivers hear different noisy versions. And can you model it by links?
So here there's no noise. The difference is that here
But
there's.
you want to replace noisy links with a big pipes, right?
I think he's asking if there are gadgets you can introduce, given that P of Y1, Y2 given X. Is there a gadget?
So there is a gadget that you can introduce, but it's not tight. So you can introduce an upper bounding gadget and a lower bounding gadget, such that the capacity of the broadcast channel will be sort of included in the capacity of this small. Yeah. Maybe I'll talk about that a little bit in a second.
Like in the classical models of Shannon, there is a part of the model or the system that is space given to you and fixed, and then there are the parts that you can optimize on.
Mm-hmm.
But here, everything is fixed, or I
The topology is fixed. The network is fixed. The communication requirements are fixed. So SI wants to communicate to TI. And what you can change is you can define the functionality, the code over the network. So that's the idea. Okay, so I lost it. Here it is. Good. So this is sort of when we're saying that R1 to RK is achievable. I'm going to call this epsilon n feasible because I'm allowing error epsilon. I have block length n. And I'm going to say that a rate vector is achievable or feasible. I'm going to use both these terms. If for every epsilon there exists some very large block length n such that I can communicate it at error epsilon, and then the capacity is going to be defined as the closure of all the feasible tuples. So these are standard definitions. Or these are the standard way things are looked at. Okay, so that was preliminaries. And now let's get to the first problem, or the edge removal problem, which was defined a few years ago by Hoefroth and Jalili. So it's a very simple problem. I have a multiple unicast network, SIs to TIs, and I know that there's some rate vector that's achievable. I can communicate over this network with rate tuple R1 to RK. And this network has a certain edge. And now I want to look at this network without that edge. And I want to ask, given the network without that edge, and let's think of the edge as having capacity delta, and usually I'm thinking of delta as being small. But you can think of delta, any delta, but usually I'm thinking of delta as being small. And I'm asking, now when I want to communicate over this new network without the edge E of capacity delta, what is the rate? With what rate can I communicate? So I know I can communicate at R1 to RK, and I'm asking how much, or can I give a limit on how much I'm losing in rate by just removing this sometimes very small link of capacity delta. So that's the edge removal problem. And it's easy to see that if you think about this problem just a little bit, that there are instances in which if I remove a delta capacity edge, I'm going to lose at least a delta rate additively in each and every coordinate. That's pretty easy to see, and I'll show an example. So I'll just do the butterfly network. So this is a kind of well-known network. It's a butterfly network, so I have source S1 wants to go to T1, source S2 wants to go to T2, and all the links here have capacity 1. And given this network, I can communicate at rate 1, 1. That is, I can bring the source of the information of S1 to T1, S2 to T2, and using this very simple scheme. So the thing is that I'm on this bottleneck edge, I'm communicating the XOR or whatever of the random variables. So this scheme allows me to communicate at rate 1, 1, and now I want to remove an edge from this network. I want to remove a delta capacity edge. I'm thinking of delta as being small, so what I'm going to do is I'm going to multiply this middle edge and put a lot of delta capacity edges instead. And if I remove one of them, then it's pretty easy to prove that I can still communicate at high rate. I can still communicate not at rate 1, 1, but at rate 1 minus delta, 1 minus delta. But the thing is, I can't communicate at any higher rate.
1 minus delta by 2, 1 minus delta by 2 is possible with time sharing, right?
I don't think so.
I think we can just route like
1 minus delta, all that by 2.
both the deltas by 2, I think it's possible. Like you could.
You can do 1 minus delta, all that by 2, that's true, but I think you can't do
1.5. Like, I think it's slightly higher than the delta. Maybe.
Yeah, I agree.
With-
the part you're not using for, the part that you would be using to match with the XOR you're now not using, like the remaining delta, the matching delta on this, this top and bottom links, you can use that for something.
So this scheme doesn't use full capacity of S1 to T2?
No, it leaves a little bit of capacity there. Okay, it could be, although I have to think about that.
No, you get
Somehow.
One might say that the cut set bound.
Yeah, it should be the cut because if you're,
Cut set bound.
okay, good. Thank you. And so, yeah, it is true that you don't use all the capacities here, but you can still.
What were the capacities in the graph? Can you remind?
In this case, there were 1, let's say, Yeah, just except the middle ones, which were delta and 1 over delta copies of them. But so you're going from 1, 1 to 1 minus delta, 1 minus delta, and so you're not losing that much. And so this was for this specific network. And sort of the question that edge removal asks is, what is the price of removing an edge in general? So what is the price of edge removal? And here's sort of the statement. Formally, I have a network A, and I can communicate at rate R1 minus R1 up to Rk. I'm removing an edge of capacity delta. Can I still communicate at rate R1 minus delta up to Rk minus delta? So that's the formal statement. And it's not known to be true in general, and it's not known to not be true. So there are no counterexamples yet for this edge removal statement. So I wanted to remark on that later, but I very strongly believed, let's say, that this is true. Not that I've been able to prove it, and I'll say something that contradicts what I just said now in a second. But yeah, so I think it's believed maybe by many to be true. So that's the edge removal statement. And it is known to be true in some settings. So I'll just describe which settings are known. And so, for example, in the multicast setting, which is sort of the first setting that was studied in network coding, in which all the sources are located at one node, and all the terminals want all the information of all the sources. In this setting, it's pretty easy to see that if you have a delta decrease, if you remove a delta capacity edge, you're only losing delta in each coordinate at most. The same kind of picture, but when the terminals may want arbitrary subsets of the sources, so this is called the co-located source case. Again, if they're co-located and terminals want some arbitrary information of the sources, then again you can do, you're losing delta in each coordinate. And if your communication function is linear, each and every one of those f's in the communication is linear, then also if you remove an edge, you can prove that this decreases the rate at most, delta in each coordinate. So it's not known to be true in general. And even a simpler question, which says, okay, maybe it's not, I remove a delta capacity edge and I'm losing exactly delta. Maybe there's some function of delta that I'm losing, maybe. And what I want to prove is that if I'm removing a little bit, I also lose a little bit. But I don't know, maybe there's some kind of function. Just a second, I'll show the asymptotic version. So even this is not known to be true, which says, if I know that I can do R1 to Rk and I'm removing a delta capacity edge, we don't know of a function f which is continuous at 0, meaning that when delta tends to 0, then this function tends to 0, so that I'm losing Ri minus this f of delta.
So you're saying it's not even known if f depends on the network?
Yeah. So the network is thought of not as the asymptotic element in this analysis. If it depends exponentially on the size of the network, that's fine. Not even known. I'm a little bit embarrassed to say this, but yes.
What was the linear, I didn't understand the definition of the linear case.
The linear case means that these encoding functions in this flow of information, each and every outgoing edge is a function of its incoming.
It's not a statement about what's received. What's received is just information, but you're saying if the design of the protocol...
If the design of the protocol is linear and I remove an edge, then I can use the same protocol essentially with some changes and lose just a little bit.
So that's known.
For the linear case, it's known, yeah. So there are a few cases, not too many, that even there are more, but I didn't state them. These are known, but in general, it's not known.
So can you say something about how interesting these proofs are, or complicated, or which ones should one read?
Are you hoping it's a disjoint set?
No, I'm hoping, the question is which ones should you read if you want to learn something interesting?
Yeah, so the general idea is that sort of, let's do two sources. You have some kind of protocol, and there's some edge you're removing. And you can sort of look at the values of this edge as a function of x1, x2 that you're communicating. And so you can have like value alpha 1, another value alpha 2, and you can think of these being spread out anywhere. And if I remove this edge and I tell the receiving node that actually what should have been transmitted was alpha 2, then I can use the same protocol. And so you would like some kind of large subset of x1 and x2 that gives you the same alpha value. But that's not possible in general, because you don't know what the protocol is. The protocol could have the communication protocol could have a very strong dependence on the value of this edge based on x1 and x2. So when things are linear, there's some structure that you can sort of use. And when things are co-located, this means that the encoding of x1 and the encoding of x2 is controlled from the same node. This means essentially, and I'll just show it very briefly, that you can randomly partition this space into these cubes which are not that large. And these cubes, for example, each and every cube is going to have at least one location in which there's an alpha 1. And now what you can do is you send your information, probably very vague, I'm not sure. The information you're sending is not an individual source value, but you're saying I'm sending something in the range here, that's my information, this range. And what the actual source node is sending is this specific value. So you can actually communicate over the network without knowing what that value of the edge is, because it's actually pre-given. So I don't know if this was...
So like the linear case, for example, you're saying would generalize to any situation where this picture can be partitioned into rectangles.
Yeah, exactly. So if you have a separable kind of a communication scheme, and you can try to define separable rigorously, then it generalizes, yeah.
Where did the error probability come into these statements? I mean, there was an error allowed.
Yeah, so the whole, I think that the standard way to define things in the information theoretic community is that you're allowing some error, but for any error that you allow, you want a large enough block length that's going to give you communication with this error. And you're allowing the block lengths to be as long as you want. And so being able to communicate means that you're able to communicate at any error, with any probability of error, as long as this decays to 0.
But we're talking here about rates as well, so
I think one way to think about this is suppose that there are some networks that have solutions only for odd number size alphabet, for example. So if the alphabet has an even size, there's no solution. For odd number, there is a solution. But according to this definition, because you allow a little error, you can still deal with the alphabets of, say, even size. Does that make sense? I mean,
Well,
I mean, let's say if the alphabet is sufficiently large, even though technically speaking there is no perfect solution, you have something that regards to some epsilon as a solution.
so it may be related, but I'm not. So the source of error is you're saying I have, let's say, give me an epsilon, I don't know, 1 over 10. I say, okay, I have a communication scheme with n equals 100, in which for a 1 over 10 fraction of the source symbols, I'm allowing an error in communication, and on 9/10 of the source symbols, I'm not allowing an error communication.
Where n means what?
N is the number of repetitions I'm allowing to use on the, yeah. So n is the parameter that sort of tends to infinity, which means how many.
That's why it's not supposed to affect rates. That's why you're.
Yeah, everything is normalized by n. So it's sort of the amortized. If we use the terminology of the first talk, it's amortized over. Okay.
There's been a lot of application complexity. So this probably depends on directed like if it was undirected, then there's only a delta gap, right? Because you can feed information back and forth.
Yeah, essentially yes. So if it's undirected and there's another path, you can sort of use this path, and maybe so there's going to be, it's not delta, but there's some, yeah. If it's undirected, you have a lot more freedom to sort of reroute the information. And if there was no way to reroute, then this is like a bridge in a graph, and then there's some other reasons for it to hold.
You're not saying that the edge removal statement is known for undirected?
Well, some versions.
It said so. Yeah, I have to be careful and say I don't think actually. Well, okay. So I'm saying almost positively yes, but I remember some delicate issue which may have to be revisited.
So for the vector and acyclic graphs, what is known for tags?
So what meaning? Nothing. There's no bound. So, I'll say that for directed acyclic graphs in general, knowing what the capacity region of a network is, it's a very open problem. So there's no sort of simple solution given R1 to Rk and given a network saying, okay, yes, I can communicate at this rate or no. So this is completely open. There are upper bounds.
But this particular statement can be done without knowing the capacity.
Yeah, it can be, and it's not known. And I'm saying, yeah, it's completely open. And one of the reasons is that there's difficulty in getting tools to sort of answer this question without knowing exactly what the capacity region is ahead of time. Well, this is at least the feeling that I.
Can you help me understand this question better? So it seems so extravagant that it seems like I could just discard delta of the capacity of all of the edges of the network, and
Yeah.
then I just have I've slowed down my whole network by a factor 1 minus delta, and then the statement seems trivial. So something's clearly.
So that's true. But if you just slow down your network but still have a connection, so you're reducing the volume of an edge.
This guy is completely gone.
This guy is completely gone. That's the whole issue is really removing it completely. So a multiplicative factor of reduction, you're right, it goes through.
So for a multiplicative factor, we understand it would be exactly scaling everything by...
Yeah, that would be exactly scaling. Yes. Yep. 5 minutes? Are you serious?
Charge the audience.
Yeah,
Wow.
I think it would be fine for you to go over... It's actually 15 minutes, because we started at 40, so then it goes to 30.
Oh, my bad.
Okay, 15? Okay. Wow, okay. Okay, so I'll say a little bit about edge removal, and then I'll try to connect it to other problems, because that's sort of the idea. And at least I think I'll at least get to 2. So it's not known, and maybe a reason to understanding why this is a difficult problem, I'll just show examples in noisy networks in which it's known not to be true. So edge removal in noisy networks is known to really affect the capacity a lot. So one example is a jamming adversary. Think of X going to Y, just point-to-point communication. There's an adversary that can flip bits, standard a model of communication in adversarial noise. Let's say I can flip a p fraction of the bits. And I'm communicating n bits, and Y gets an error of a p fraction of these n bits. If I allow a very low rate channel between X and Y, which sort of sends the hash of X to Y, then I can communicate over this channel not using a protocol, for example, list decoding. So I can send information over the channel such that Y list decodes and then disambiguates using this hash. And again, I'll say the objective is unique decoding. And if I send information using a list decoding protocol, I can list decode using the information on this edge and then get a unique value from the information over this hash. And the thing is that there are significant differences between list decoding and unique decoding. So removing this edge has a large effect on capacity. So that's for the adversarial noise, it's pretty clear that even a negligible edge, it could be log n bits out of a block length of n, it's enough. And even when the channels are memoryless,
Excuse me, but here the adverse if, so it was assumed that if there is, the edge is there, that one is not affected by the adversary?
yeah. So I'm saying in this toy example, in which I have an adversary that can affect one of the links, but there's some kind of side information that maybe costs more, so I'm just sending log n bits through a secure channel or whatever, then I can sort of reduce from this decoding to unique decoding. And removing this is an example that edge removal can affect things a lot. And even in this memoryless case where I have a multiple access channel, this is some probability giving y, given x1 and x2, and x1 and x2 are thought of as independent encoders, and y wants to get the value of x1 and x2 after the end. So the capacity of this channel, or the rate of communication through this noisy network is well understood. But if we add something we call a cooperation facilitator, in which I take x1, x2, give them to a node that gives me very low rate, again, negligible rate back to x1, x2, and then I communicate over the MAC. So I'm allowing some kind of cooperation between x1 and x2 through this very low rate channel. Even in this channel, which is a memoryless channel, it's not an adversarial setting, it's a sort of random error setting, then we can show a significant difference between capacity if you have the edge or you don't have the edge. And to be a little bit more precise, we can sort of show that the edge removal statement doesn't hold, but for this case, the asymptotic one still holds. So it's still true that if this is negligible, I'm going to get a negligible change in rate, but the connection is not linear.
Yeah, but this is channel coding. So as if you had the source depending on the channel. So because your code rate sets depend on what you know about the channel.
Yes.
And in your network coding model, you don't have that. The sources are given and fixed.
So the sources are thought of as being completely uniform, and the channels don't have any noise. So, what you do know is the topology of the network. It's a different setting. No, I'm not saying that this sheds light on the other. I'm just saying that removing edges in networks is something to take seriously because it can affect a lot, even if you remove something of negligible capacity. Okay, so that's the edge removal, and it's sort of open. I try to sort of give a hint why it's not clear how to prove that this edge removal statement holds. And the essential thing is that if I get a code for communicating over a network with a certain edge, it's really not clear how to design a code to communicate without that edge. It's just the tools that we have, at least the ones that I've been playing around with, are not successful. But the theme of this talk, or what I'll get to a little bit, is to show what the implications are. So if I assume edge removal is true, or if I assume it's false, what does it affect? So that's the idea. So edge removal is not known, but I want to know what the implications of solving this problem are. So I won't get very far, but I'll show at least two examples, and I hope offline people can ask me. So still give me a 5-minute mark, I'll see. So here's the first problem I want to connect to edge removal. And this is the 0 versus epsilon error communication problem. And I hope this also ties to things that were discussed here in interactive communication, because I understand that also there's like some kind of tension between allowing an error and not allowing an error. So what is the problem? Again, I'm giving a network. I have k sources, k terminals. I'm communicating over this network, and I can achieve rate R1 to Rk over the network. I can achieve it when I'm allowing negligible error. So again, for each error, there's a protocol. That is, there's a block length n that allows me communication with that error, and I can do this for any error tending to epsilon, tending to 0. And now I want to insist on 0 error. I don't want to have epsilon error. I want to insist on 0 error, and I want to ask, what is the rate that I can achieve with a 0 error? So that's the second problem I want to discuss. What is the cost and rate when I insist on 0 error instead of epsilon error? So just like previously, for some cases, this is understood. So before that, actually, I want to show that, as previously, that this is a question that one has to take a little bit seriously, in the sense that if I'm not in the network coding regime, then this doesn't hold. I didn't even say what the question is yet. Okay, so the question is, can one obtain a higher communication rate when allowing epsilon error as opposed to zero error? Yeah, I didn't even state what the question I want to ask is. And the thing is that if I'm not in the network coding regime, the answer is yes. If the channels are noisy, then allowing a little bit of error helps a lot. And if the sources are dependent, then again, allowing a little bit of error helps a lot. And we saw Slippy and Wolf mentioned in the previous talks. So for example, if I have two sources that are dependent and I have capacitated edges, and I want Y to decode both sources, then allowing myself to have an error on source realizations which are not typical is very crucial to get this rate through. So the answer is yes. There's a big difference between epsilon error and zero error in general. And the question here is, in the network coding setting in which all the sources are independent and the rate and the channels are noiseless, is there a gap between epsilon and zero error? So again, what is the advantage in epsilon error over zero error for general network coding? That's the question, the second question I want to ask. And now what's known, again, this will be the formal statement. If I have a network that's R1 to RK feasible when I allow a little bit of error, then I want to say that if I want to go from that protocol to a protocol with zero error, I'm losing some delta, which is a function of epsilon, and delta should tend to zero when epsilon tends to zero. That's the idea. So the same thing is known. So for multicast, the statement is true. And actually for multicast, which is the first form of network coding that was studied, it was shown, an optimal protocol was shown with zero error. And so it was optimal based on cut set bounds, so you can't get any better than that. And I think from that point on, it's sort of nice to see historically people think of this communication setting in network coding as being as a zero error communication setting, and didn't really consider if there is an advantage or not in epsilon error. So we're asking here if there's an advantage. So for multicast there isn't. For co-located sources, also you can show that there's not such an advantage. And for linear codes, even if only the encoder is linear and the decoder is not linear, again you can show that there's no advantage in allowing error than insisting zero error. And we're asking if the statement is true in general, and we want it to be true for any function delta that tends to zero when epsilon tends to zero. So I don't know, I think maybe, I don't know who asked, but okay, so I was studying the edge removal problem, and I was sure that the edge removal problem is true, and we were trying to prove that it's true. And I was studying the epsilon versus zero error problem, and I was convinced that the epsilon versus zero error problem, 5 minutes, is false, meaning that there is an advantage in epsilon error, but it turns out that these two are actually the same question. So edge removal, you can connect edge removal to the zero versus epsilon error.
So you said did the same question in the same direction?
Yeah.
So you guaranteed yourself?
I guarantee myself that I'm both wrong and right, so that's, yeah. So edge removal is true if and only if the zero versus epsilon error in network coding is true. So this would be, for example, you have to prove both directions, but this would be, for example, one direction. And here I'm not differentiating between the asymptotic version or not, but here we're saying that if the asymptotic edge removal statement is true, then actually I can go from any network coding solution with epsilon error to a network coding solution with zero error with negligible cost, with cost which depends on epsilon but tends to zero. And the way to prove this is via reduction, in a sense that we sort of assume that our network has epsilon error. We also assume that this asymptotic edge statement holds, and we prove the statement. So this is kind of trivial. And the proof, I won't go through it, but I'll be happy offline to sort of show it. It has these kind of rectangle or blocking ideas inherent in the proof. And so that's one direction, and we do the other direction also. So that's one connection between edge removal and zero versus epsilon error. So now I have to choose another problem, because we're not going to get through all of them. And so I think people were talking a little bit here about index coding, so I'll move to the index coding regime. So I'm going to jump to a different problem. Maybe at the end I'll just mention what, sorry for these quick slides. Somehow I was sure that I would finish this talk in 35 minutes, but okay. So again, we have the edge removal problem, and now I want to connect it to another problem. And this problem is sort of the problem of representing networks by a simplified model. So there have been some recent studies that show that any network coding instance can be reduced to a very simple instance of network coding called index coding. And this was shown first by, it was shown to be true for linear functions, and then it was shown for in general. And in essence, it says, give me a network coding instance. I'll turn it into an index coding instance in such a way that solving this instance will solve my network coding instance. And an index coding instance is a special case of network coding. It can be drawn by this graph, which has all the sources. It has the same number of sources in terminal. Source I wants to communicate with terminal I. All the sources can sort of broadcast information through this single link to all terminals, and in addition, terminals get what's called side information. So it's a broadcast with side information problem. And so there's an efficient reduction taking network coding to index coding, and it's kind of nice in the sense that this whole issue of network communication is some kind of combination of topology, which is the topology of our networks, and information. So you have to encode information with the sort of restrictions that the topology of the network give you. So it's a mixed up problem with these two very difficult aspects on their own. And so this reduction somehow separates, I think, information from topology. And the reason is that this node here, in this index coding world, is the only node that does encoding. So you're encoding information without actually any topological constraints. You do have constraints on the decoding, which is where how the equivalence is proven, but still, at least, it sort of conceptually simplifies things because all the encoding is done with no constraints on topology. Okay, so that was shown, a connection between network coding and index coding. And the theorem sort of looks like this. It says that give me a network code. I can construct an index code such that if the network code is R feasible for some R, then there's some predefined function f. Then the index code is R prime feasible for this function, for this f of R. So f is a very simple function, part of the reduction. And we call this reduction a reduction in code design because it allows to construct a code for the network code given a code for the index code, a specific code. A very related question, which is of significant interest in the information theory community, is can one determine the capacity of a network code given the capacity of an index code? And the capacity is just the closure of this all achievable rate.
Excuse me. In the reduction, the number of sources and terminals also changes?
Yeah, so in the reduction, there's a very large blow-up. It's polynomial still, but if I have a network with, let's say, I use n for the nodes and m for the edges, then the number of sources here is sort of n plus m, something like that. So the dimension gets a lot larger. And actually, because of this blow-up in dimension of this rate vector, this function is actually expanding a k-tuple to something a lot larger, then this reduction actually breaks down. It completely breaks down when you want to study this reduction and say that maybe this reduction actually preserves capacity and not only code design. So it's a very subtle difference. Sort of one is the closure of the other, but I can maybe try to explain this offline. The fact that we're in higher dimensions here than there means that the closure operation doesn't sort of transfer directly. Okay, so I just want to say that there's interest in connecting the network coding capacity region to the index coding capacity region. It's not known how to do this. all attempts break down, and again, you can connect this to the edge removal problem. And you can connect this in a very strong manner, in the sense that you can show that this asymptotic edge removal statement is true, again, if and only if one can determine the capacity region of a network code with that of an index code. And so one direction is very general, the other direction, this statement is a little bit more delicate in the sense that this reduction allows to communicate network coding capacity with index coding capacity if and only if the edge removal statement is true. So in this direction, we're actually thinking of a specific reduction in going in the opposite direction. But edge removal plays a strong role. So I'm going to sum up. I know that I'm out of time. I'll just at least state the other problems that I wanted to connect to, and I can do this offline. So let me try to go to the summarizing slide, which I think is, let me guess. Okay, good. So this is like a meta slide, which says the following. I have a network, and I want to change the model of study very, very slightly. One way to change the model is to remove a very small capacity edge. So things are perturbed a little bit. I'm just removing one small edge. Another way to change the model is to say, okay, I don't want epsilon error, I want zero error. I'm just changing something very slightly. Another way to sort of change the model is what we saw with capacity, is to say, okay, I want to design a code is one problem, but maybe I want to understand if this rate vector is in the capacity region. That's another problem. And I didn't show this at all, but you can also change the model a little bit by saying, okay, usually the sources are independent, but maybe if I allow a very slight dependence between the sources, that's another model. So all these perturbed types of models, it turns out that they're completely equivalent. So all of them are equivalent to network coding, and there's some kind of theorem that's evolving that's not completely formally stated here, is that all these forms of slackness can sort of reduce one to the other. You don't have to study, if you study one of them and understand one of them, you actually understand all these forms of slackness. So this is sort of the beauty that I see in this edge removal problem, in the sense that it is kind of canonical when we thought of these canonical problems, and it's related to many other problems. So I hope this wasn't too vague, because I didn't get to define other problems here. Yes, I think I'm sort of out of time anyway, but the objective of this talk is to just say that, you know, the bread and butter of computer science, cryptography, is this massive use of reductions as a tool. And here it's just evolving information theory, and I think it has great potential, and this is just one example that we've been showing, and there are many others that have started to evolve recently. So that's hopefully the bottom line. Okay, thanks.